The two-factor ANOVA is a widely used technique. It's used when we have the question, what is the association between factors and the means of groups that have values for those factors? The approach is to conduct an analysis of variance, which is where the ANOVA name comes from. If you're not familiar with the one-factor ANOVA, I recommend watching the Stats Examples videos on the one-factor ANOVA. There's also a video that introduces the two-factor ANOVA and spends more time talking about what all the values we'll be calculating represent. In this video, we'll look at two step-by-step examples of how to do all the calculations and interpret the results from a two-factor ANOVA analysis. But let's do a quick review of how the test works first. If you want to skip straight to the calculations, jump to the time point in the arrow. Assuming you've stuck around, let's look at how we do the ANOVA in general. The ANOVA has a pair of conceptual hypotheses which illustrate the question we have about whether there are associations or an interaction between two factors we're looking at and the means of the groups with those factors. The null hypothesis is that there are no associations or an interaction, whereas the alternative hypothesis is that there is at least one genuine association or interaction. We test these conceptual hypotheses by using a set of practical null and alternative hypotheses. Our first practical hypothesis focuses on just one of the factors, call it factor A, and asks whether the mean sums among for the A factor is equal to or less than the mean sums within. The null hypothesis is that it is. This would indicate that factor A is not associated with differences in the means of groups. The alternative hypothesis is that the mean sums among for the A factor is larger than the mean sums within, which indicates a relationship between factor A and the means of the groups. This is basically just the one-factor ANOVA, but ignoring the second factor entirely. Our second practical hypothesis is exactly the same, but for the second factor, factor B. The third practical hypothesis examines whether the mean sums among due to the interaction between the factors is equal to or less than the mean sums within. The null hypothesis is that it is, which would mean no interaction. The factors act independently of one another. The alternative hypothesis is that the mean sums among for the interaction is larger than the mean sums within, which indicates that the factors aren't independent. Any effects of one factor depend on the value of the other factor. To statistically test the practical hypotheses and answer our conceptual hypotheses, we'll perform 4 steps. Step 1. Perform an Fmax test to ensure the equality of variances. The two-factor ANOVA is a homoscedastic test and requires equal variances in the groups. Step 2. Calculate the sums of squares terms and the degrees of freedom values. These will go into our ANOVA table. Step 3 is to complete the ANOVA table. First, we calculate the mean sums values by dividing each sum of squares values by the degrees of freedom. Then we calculate 3 F values for 3 F tests. F sub A to test for the association with factor A, F sub B to test for the association with factor B, and F sub int to test for the interaction between the factors. These F tests are all similar to the one-factor ANOVA. Lastly, we determine 3 p-values and reject or fail to reject each null hypothesis based on these values. Step 4. If any null hypothesis is rejected, we usually create a pair of interaction plots to look at so we can figure out how the significant associations or the interaction behave. Step 1 is exactly the same as for the one-factor ANOVA, so let's look at steps 2 through 4 in more detail. First, let's diagram how to get the sums of squares values. Let's imagine we have a situation with 6 groups as shown, where there are 3 values for the color factor, green, purple, and orange, and 2 values for the shade factor, light and dark. We set up our data table with columns corresponding to one factor, the color one in this case, which we'll call factor A. The data table also has sets of rows that correspond to the shade factor, factor B, the top rows for dark and the bottom ones for light. To calculate the overall sums of squares, SST, we combine all the data into one huge data set and calculate the sum of squares of all these values. This is exactly the same as the one-factor ANOVA. To calculate the sum of squares within, we calculate the sums of squares values separately for each of the groups using each group's mean and sum them. This is also exactly the same as the one-factor ANOVA. The diagram at the top illustrates how the sum of squares values for the factors combines the groups for the other factor and only analyzes the differences between the groups that vary for the factor we're interested in. To calculate the overall sum of squares values for factor A and factor B, we calculate sums of squares of the mean values of each factor value, compared to the overall mean, then multiply by factor sample size, lowercase n. We usually subtract these two values, along with the SSW, from the SST to get the sum of squares among value for the interaction. We also need to determine the degrees of freedom values. For j different values of factor A, and k different values of factor B, and n values in each of the groups, we use the following equations. The degrees of freedom for factor A is the j different values for A minus 1. The degrees of freedom for factor B is the k different values of B minus 1. In the example to the right, there are 3 different values for factor A, green, purple, and orange, so we have 3 minus 1 equals 2 degrees of freedom. And there are 2 different values for factor B, light and dark, so we have 2 minus 1 equals 1 degree of freedom. The degrees of freedom for the interaction is j minus 1 times k minus 1. For the example to the right, that's 2 times 1 equals 2 degrees of freedom for the interaction. The degrees of freedom for the within group is the total number of data values minus the number of groups, which is capital N minus j times k. The degrees of freedom overall is capital N minus 1. The mean sums among values come from these equations: the sum of squares values divided by the degrees of freedom for each factor and the interaction. We then do 3 f-tests, comparing each mean sums among value to the mean sums within. These are the f-values we compare to our critical f-values to determine whether the p-value for our test is less than 0.05 or not. The data from our calculations are usually presented in an ANOVA table, as shown, with columns for the degrees of freedom, sums of squares, mean sums, f-values, and p-values for the f-tests. The different sources of variation are in the rows. We indicate the p-value for each of our 3 f-tests, and these indicate any significant associations between factors in the means or significant interaction. Note that this table shows the sums of squares values, but since you can figure that out from the mean sums and degrees of freedom, this column is often omitted when these tables are published. We have just one more thing to do. After the ANOVA table is made, we generally create interaction plots. What we do is make a pair of plots with group means on the y-axis and different x-axes. Values of factor A on one plot and values of factor B on the other plot. This allows us to do 2 things. First, we can combine the visual patterns with the results from the ANOVA table to distinguish random associations between the factors and the means from non-random ones. Each of the 2 plots is good for helping us understand what association the factor on the x-axis has with the group means. Second, the plots allow us to get a sense of what any statistically significant interaction looks like. Note that the figures will almost always appear to show some patterns or interactions, but the results of our f-tests are what tells us if these are real or just noise due to random factors. Now let's look at a couple of concrete examples. For our first example, let's think about a situation in which a medical researcher is interested in the details of the placebo effect, the phenomena whereby patients prescribed benign medications, sugar pills for example, seem to improve almost as well as if they had been given pharmacologically active substances. Specifically, she's interested in whether a person's trusting nature, as measured by a standardized psychological test of this personality trait, influences the placebo effect or not. She administers the psychological test to 30 study subjects and uses it to divide them into 2 categories, low and high levels of trusting nature. For each of these categories, she divides subjects randomly into 3 treatments: a control group that doesn't get a pill, a group where a placebo pill is received, and a group where the FDA-approved drug is received. The FDA-approved drug influences a measurable statistic called ADT, which she measures in all the study subjects after the treatment. For this 2-factor ANOVA, one factor will be the psychological category, and the other will be the treatment. The interaction is whether the effect of the drug versus placebo versus control depends on the psychology of the subject, and this is what the researcher is most interested in. Imagine that the data from the study looks like this. We've used the 2 trusting values for the columns, and the 3 treatments correspond to sets of rows. Of the 30 subjects, 15 were classified in each trusting group. Of the 15 in each group, 5 were randomly assigned each treatment. The values shown are the ADT scores. Step 1 is the F-max test for equality of variances. If you're unfamiliar with this test, you can check out the Stats Examples video on this channel, which describes the test in more detail. For this, we calculate the means and variances for each of the 3 times 2 equals 6 groups as shown. The F-max value is the largest variance divided by the smallest variance, 23.5 divided by 8.5 in this case. This gives us an F-max of 2.765. The critical F-max value for 6 treatments having 4 degrees of freedom each and an alpha value of 0.05 is 29.5. The calculated value of 2.765 is less than 29.5, therefore p is larger than 0.05, and the variances can be treated as equal, and we can do the ANOVA. Note that the values we calculated are useful for later. For the means, we can keep these values for making our interaction plots and data figures. For the variances, we can keep these values for quickly calculating the sums of squares within value. Step 2 of our 2-factor ANOVA is to calculate the sums of squares and degrees of freedom values. First up is the sum of squares total. The SST comes from all the values compared to the overall mean. The first step is to look at all 30 values in our data table and calculate the mean, which is 18.5. Once we have this, then the overall SST will use each of the values in the table, so we get 10 minus 18.5 squared plus 14 minus 18.5 squared plus 15 minus 18.5 squared plus the rest of the values in the table, to finish with 18 minus 18.5 squared plus 15 minus 18.5 squared. That gives us 72.25 plus 20.25 plus 12.25 plus all the other values in the table plus 0.25 plus 12.25 for an overall sum of 759.5. The degrees of freedom for the SST is the 30 data values minus 1, which equals 29. The next sum of squares value is the sum of squares within, which comes from the sum of squares for each group, where the values are all compared to the mean for their group. This was one reason to save the means from before. For example, the sum of squares within for the control treatment, low trusting group, would use the 5 values in that group compared to the mean of 16 for that group. This is 10 minus 16 squared plus 14 minus 16 squared plus 15 minus 16 squared plus 18 minus 16 squared plus 23 minus 16 squared for a total of 94. Likewise, the SSW for the control treatment high trusting group is 38. The SSW for the placebo treatment low trusting group is 46. The SSW for the placebo treatment high trusting group is 34. The SSW for the drug treatment low trusting group is 94. The SSW for the drug treatment high trusting group is 66. Note that since the variance is the sum of squares divided by the degrees of freedom, we could get these values from our variances we calculated earlier for the Fmax test by multiplying each variance by 4. We add all these together to get an overall sum of squares within of 372. The degrees of freedom for the SSW is the 30 data values minus the 6 groups, which equals 24. So far, these two sums of squares calculations are the same as for the one-factor ANOVA, but the next 3 values, the sum of squares among values, are where things get a bit different. The sum of squares among values come from comparing the data for the factors to the overall mean, similarly to how the overall SSA is calculated in the one-factor ANOVA, but the definition of the groups differs somewhat. For the SSA for the trusting factor, we consider the dataset as if it's just 2 groups, one for each trust value. The SSA trust value comes from the means for each trust group compared to the overall mean, weighted by sample size. From before, the overall mean is 18.5. The means for each value of the trusting factor are 20 and 17. The SSA trust is therefore 15, the number of values in the low trust group, multiplied by 20 minus 18.5 squared, plus 15 times 17 minus 18.5 squared. After a couple of steps, we can see that this gives us a sum of squares among for the trusting factor of 67.5. The degrees of freedom for this SSA is the 2 groups minus 1 equals 1. The sum of squares among value for the treatment group works the same way. The SSA treat value comes from the means for each treatment group compared to the overall mean of 18.5, weighted by sample size. The means for each value of the treatment factor are 15.5, 18.5, and 21.5, and there are 10 values in each treatment group. The SSA treat is therefore 10 multiplied by 15.5 minus 18.5 squared, plus 10 times 18.5 minus 18.5 squared, plus 10 times 21.5 minus 18.5 squared, and after a few steps, we get 180. The degrees of freedom for this SSA are the 3 groups minus 1 equals 2. The last sum of squares among value is more complicated to understand and calculate. For the SSA interaction, it comes from the weighted squared differences between each group and the expectation based on group and overall means. In practice, it's easier to get by subtraction. We'll show both methods. To get the SSA interaction, we'll use the means for each of the factors. These are the values from earlier. We'll be using these along with the means for the 6 different combinations of factors. The first term in the SSA interaction calculation will be the sample size of the first combination, 5, times, in parentheses, 16 minus 20 minus 15.5 plus 18.5 squared. If we think about what this represents, it shows how different the observed mean is from what's expected based on the factor means and overall mean. Deviations indicate non-independence of the factors and interaction. The other 5 terms work the same way, comparing the mean for each of the combinations of factors to the factor means and the overall mean. When we calculate this all out, we would get 140. There's a second method to get the SSA interaction. The overall SST is the sum of the SSW and the 3 SSA terms. Rearranging this allows us to solve for SSA interaction, and then we can plug in the values we previously calculated to also get 140. The degrees of freedom for the interaction is the number of groups for each factor minus 1 and then multiplied. 3 minus 1 times 2 minus 1 gives us 2 degrees of freedom. Now we can start step 3, completing the ANOVA table. The table shown here has the sum of squares and degrees of freedom values we just calculated. To get the column of mean sums values, we just take each of the sums of squares values and divide by the degrees of freedom for that row. That gives us these values. The next step is to divide each of the 3 mean sums among values by the mean sum within to get the F calculated values. That gives us these values. Now we have 3 F values, and we'll do 3 F tests. If you're unfamiliar with the f-test, you can watch the stats example video on the f-test. For the trusting factor, the f-value is 4.355, with 1 degree of freedom in the numerator and 24 degrees of freedom in the denominator. Looking at tables of critical f-values for alpha of 0.05 and 0.025, we see that the p-value will be less than 0.05, but more than 0.025. With a computer, we can get an exact p-value of 0.048. For the treatment factor, the f-value is 5.806, with 2 degrees of freedom in the numerator and 24 degrees of freedom in the denominator. Looking at the tables of critical f-values, we see that the p-value will be less than 0.025, and the computer gives an exact p-value of 0.009. For the interaction, the f-value is 4.516, with 2 degrees of freedom in the numerator and 24 degrees of freedom in the denominator. The tables tell us that the p-value will be less than 0.025, and the computer gives 0.022. This tells us that there are significant associations between the mean value of groups and both their trusting factor and treatment received. There's also a significant interaction. But what are the associations and the interaction? To understand what our results from the ANOVA table indicate, we need to make a pair of interaction plots. I put the p-values and the means of the groups on the right so we can refer to them. For the first plot, we choose one factor to be in the x-axis. In this case, it's the trusting factor. Then we plot the mean values for the groups with each value of the other factor and connect their symbols with lines. The means for the control groups are 16 and 15. The means for the placebo groups are 18 and 19. The means for the drug groups are 26 and 17. This figure is most useful for seeing how the trusting factor is associated with differences in the mean. For the second plot, we choose the other factor to be on the x-axis, the treatment factor. The means for the low trusting groups are 16, 18, and 26. The means for the high trusting groups are 15, 19, and 17. This figure is best for showing how the treatment factor is associated with differences in the mean. Any pattern we think we see is only genuine if the results from our ANOVA table gave significant results. Any non-significant pattern is the kind of thing we would easily get just from sampling error and noise. To visualize how each factor works separately, we mentally combine the groups and look at the overall pattern like this. From this, and our first two f-test results, we can say that the mean ADT significantly decreases as the trusting factor goes from low to high, p equals 0.048, and the mean ADT significantly increases as the treatment goes from control to placebo to drug, p equals 0.009. The interaction is a little trickier. We have to identify ways in which the means deviate from the expectation coming from the separate factors. There's a significant interaction. The difference in the means of the drug and placebo treatments, i.e. increase or decrease, depend on the trusting factor, p equals 0.022, or the difference between the means of the low and high trusting groups, i.e. increase or decrease, depends on the treatment, p equals 0.022. Which way we think about it is really up to us, and the most useful interpretation for whatever it is we want to use this data for. We can put all this together in an overall summary like this. Here's our original data, organized in a data table. From that, we got our ANOVA table. Note that here I've eliminated the column for the sums of squares values for the reason I described at the beginning of the video. Although we often use interaction plots to interpret our results, when we present them, it's more often in a bar chart like this, showing the means and standard errors. The ANOVA table f-test results and the figures allow us to make these statements about the associations between our two factors, trusting nature and drug treatment, and the mean ADT measured, as well as identify any interactions between the factors. Let's look at another example, one where not every f-test will be significant. For our second example, let's think about the following scenario. An ecologist is interested in the factors that influence the body size of the fruit fly, Drosophila melanogaster, in various habitats. Drosophila are known to consume rotting fruit, and he's interested in whether the fruit they eat may be important. Other studies have shown that the environment, as measured by latitude, may also be important, so he wants to include this possible factor as well. He collects and weighs flies from orchards that grow different types of fruit from sites in 3 different countries. Based on the main fruit crop being grown in the orchards, he designates 3 values for the fruit factor: apple, banana, and citrus. Based on the country the orchards are located in, he designates 3 countries for the environment factor: Mexico, USA, and Canada, which vary in latitude. For this 2-factor ANOVA, one factor will be the fruit and the other will be the environment, and the interaction is whether the effect of the fruit depends on the environment and vice versa. The data from this hypothetical study looks like this. We've used the fruit factor for the columns and the environment factor for the sets of rows. For this unrealistically small study, we'll assume that he collects 4 flies in each of the 9 locations, and the values shown are the masses of the flies in milligrams. Step 1 is the Fmax test for equality of variances, so we calculate the means and variances for each of the 9 groups as shown. The Fmax value is the largest variance divided by the smallest variance, 6.67 times 10 to the minus 4, divided by 0.67 times 10 to the minus 4, for an Fmax of 7.0. The critical Fmax value for 9 treatments with 3 degrees of freedom each and an alpha value of 0.05 is 93.90. The calculated value of 7.0 is less than 93.9, therefore p is more than 0.05, and the variances can be treated as equal, and we can do the ANOVA. As before, we'll keep the means and variances because they'll be useful later. Step 2 is to calculate all the sums of squares and degrees of freedom values. As before, the SST comes from all the values compared to the overall mean, which for this dataset is 0.2300. This gives us SST equals 0.26 minus 0.23 squared, plus 0.23 minus 0.23 squared, plus 0.24 minus 0.23 squared, plus the same thing for the rest of the values in the table. That gives us an overall sum of 0.0134 once we calculate it all out. The degrees of freedom for the SST is the 36 values in our table minus 1, which equals 35. Now for the sum of squares within, which comes from the sum of squares for each group using the mean for each group. The sum of squares within for the Mexico and Apple group uses the mean for the group of 0.25 and the 4 values. This is 0.26 minus 0.25 squared, plus 0.23 minus 0.25 squared, plus 0.24 minus 0.25 squared, plus 0.27 minus 0.25 squared, for a total of 0.001. We would do the same thing for the other 8 groups. Feel free to pause the video if you want to make sure you can see where all the numbers come from. Now we add all these together to get an overall sum of squares within of 0.0086. The degrees of freedom for the SSW is the 36 values minus the 9 groups, which equals 27. Now for the sum of squares among for the fruit factor, the sum of squares among for the environment factor, and the sum of squares for the interaction. The sum of squares among for the fruit factor comes from the means of each fruit compared to the overall mean, weighted by the sample size. From before, the overall mean is 0.23. The means for the columns that represent the overall data for each fruit factor are 0.2367, 0.23, and 0.2233. The SSA fruit is therefore 12, the number of values in each fruit group, multiplied by, in parentheses, 0.2367 minus 0.23 squared, plus 12 times 0.23 minus 0.23 squared, plus 12 times 0.2233 minus 0.23 squared. With a little bit of calculating, we can get a value of 0.00107 for the sum of squares among for the fruit factor. The degrees of freedom for this SSA is the 3 groups minus 1 equals 2. The sum of squares among value for the environment works the same way. It comes from the means of each country compared to the overall mean, weighted by the 12 values for each environment group, and using the overall mean of 0.2300. The means for each group in the environment factor are 0.24, 0.23, and 0.22. The SSA environment is therefore 12 times 0.24 minus 0.23 squared, plus 12 times 0.23 minus 0.23 squared, plus 12 times 0.22 minus 0.23 squared, to give us a sum of 0.0024. The degrees of freedom is the 3 environments minus 1 equals 2. As before, when thinking about the SSA interaction, there's the hard way and the easy way. The hard way is using the fact that the SSA interaction comes from the weighted squared differences between each group and the expectation based on group and overall means. We compare each group mean to the means for its factors, and the overall mean is shown, and if we do that, we get a value of 0.00133, but only after a lot of calculating and chances for making mistakes. Alternately, we look at the equation that relates all the sums of squares terms and rearrange to get SSA interaction equals the sum of squares total minus the sum of squares within minus the sum of squares terms for each factor. This gives us 0.0134 minus 0.0086 minus 0.00107 minus 0.0024 equals 0.00133, which is the same as the previous result. The degrees of freedom for the interaction is 3 minus 1 times 3 minus 1, which is 2 times 2 equals 4 degrees of freedom. Now for step 3, where we complete the ANOVA table. We start with the sum of squares and degrees of freedom values we just calculated. To get the column of mean sums values, we take each sum of squares value and divide by the degrees of freedom for that row. That gives us these values. The next step is to divide each of the mean sums among values by the mean sums within to get the F calculated values. That gives us these values, and now we do the 3 F tests. For the fruit factor, the F value is 1.674 with 2 degrees of freedom in the numerator and 27 degrees of freedom in the denominator. Looking at tables of critical f-values, we see that the p-value will be larger than 0.05. With a computer, we can get a p-value of 0.206. For the environment factor, the f-value is 3.767, with 2 degrees of freedom in the numerator and 27 degrees of freedom in the denominator. Looking at tables of critical f-values, we see that the p-value will be less than 0.05, but more than 0.025, with an exact p-value of 0.036 according to the computer. For the interaction between the factors, the f-value is 1.047, with 4 degrees of freedom in the numerator and 27 degrees of freedom in the denominator. The tables tell us that the p-value will be larger than 0.025, and the computer gives us 0.402. This tells us that there's a significant association between the mean weight value for the groups and the environment, but not the fruit. There is also no significant interaction. But what does the one significant association look like? Now we need to make a pair of interaction plots. Again, I put the p-values and the means of the groups on the right so we can refer to them. For the first plot, we choose the fruit factor values to be on the x-axis, and we plot the mean values of the groups, with each value of the environment factor given a different symbol, and we connect the symbols with lines. The means for the Mexico groups are 0.25, 0.24, and 0.23. The means for the USA groups are 0.23, 0.24, and 0.22. The means for the Canada groups are 0.23, 0.21, and 0.22. This figure would be useful for seeing how the fruit factor is associated with differences in the mean, but our non-significant result tells us that the apparent downward trend is probably just due to random chance, not a real relationship between the fruit and the mean size of the flies. Our written conclusion will be, the fruit present has no significant association with the size of the Drosophila, p equals 0.206. For the second plot, we plot the environments on the x-axis and the mean values for the fruit groups connected by their symbols with lines. The means for the apple groups are 0.25, 0.23, and 0.23. The means for the banana groups are 0.24, 0.24, and 0.21. The means for the citrus groups are 0.23, 0.22, and 0.22. This figure is useful for showing how the environment factor is associated with differences in the mean. As we move from Mexico to the US to Canada, the mean size decreases, and our significant results from the ANOVA tells us that this decrease is probably real and not just due to sampling error in the samples we collected. The mean weight of the Drosophila significantly decreases as the environment has a more northern latitude, p equals 0.036. In other words, the closer to the equator, the larger the flies. Finally, while it may appear that there is an interaction between the factors from the lines not being parallel, our non-significant result from the ANOVA tells us that these apparent patterns probably aren't real and are just noise. We would write this as, there's no significant interaction, p equals 0.402. Any effects of latitude or fruit are independent. Our final overall summary reads like this. Here's the original data, organized in a data table. From that, we got an ANOVA table. The table shows us that the environment factor is significant, but the fruit factor isn't, and there's no interaction. The data looks like this when presented as a bar chart, and we know from our ANOVA results that the apparent downward trend is statistically significant. The ANOVA table F-test results and the figures allow us to make these statements about the associations between environment, fruit, and the mean size of Drosophila collected from those areas. A high-res PDF version of this summary screen is available on the Stats Examples website. This is YouTube, so you know what to do. Like, share, and subscribe if you found this video useful.